Alright, so we're looking at some partial pressures and looking to solve out a couple more problems here. Again, just some various problems looking at partial pressure. First one says, number 3 says, the study of an effects of certain gases on plant growth requires a synthetic atmosphere composed 1.5 mole percent of carbon dioxide, 18 mole percent oxygen, 80.5 mole percent argon. Now, the idea of mole percent isn't as common as just say a mole fraction. Not sure why. A mole percent is based off a fictional 100, so by saying it is going to be 1.5 mole percent is like 1.5%. So if you had a fictional 100, then it would be 1.5, and the mole fraction is just move over 2 spots, 0.015. So all the mole percents add up to 100. So we got 1.5, we got 18, we got 80, all up to 100. Whereas always mole fraction adds up to 1. So they're basically the same thing. So what's the mole fraction of each? Well, this is the mole fraction of this guy. It would be of the CO2. The O2 is 18.5, 18 solid percent, and then that's 0.18 mole fraction, and then the nitrogen, 80% mole percent argon. Well, apparently they're going to use argon as an inert gas rather than one that would involve nitrogen gas. But either way, we'll go with the problem says here. We have argon, and that would be 80.5%, which is 0.805 mole fraction. And note these should add up pretty close to 1. If they don't, that's okay, but pretty close to 1. So A is done. Will be calculate the partial pressure of O2 mixture in a partial total pressure atmosphere that's 745. Okay, so proportionally speaking, you could say, well, if 745 is the total pressure, then what percent of that is due to the oxygen in the sense of pressure is concerned? So there's a lot of ways to do that. You could say, well, if you have typical linear proportion, so if we want to know what over 745 equals essentially 18 over 100, because we know 18 is out of 100, so cross multiply and divide. That tells us what portion of that would be 18 times 745 divided by 100 gives me X, or the partial pressure is 134 millimeters of Hg. Of course, there are other mathematical ways to do it. We could take the 0.18, which is the mole fraction, and then we could multiply that times the total. Same thing. All right. C says if there is an atmosphere, if this atmosphere is to be held at 120 liters in space, 295, how many moles of O2 are needed? All right, so C is looking like we got a PIV problem here. PV equals nRT, and I want to solve for moles. All right, so that's N equals PV over RT. It's saying the pressure. Okay, so pressure, I want to use just the pressure of the O2. And in this case, that's going to be 134 millimeters of mercury. 134 millimeters of mercury times the volume, which we're saying is 120 liters. Now R here, I used 0.0821 in a previous problem, but since we're using torr here, it's 62.4. And the temperature is going to be the temperature of the system, 295. Again, I have my entire sample here, and only a small portion of it is doing the O2, and that's the portion I'm using because of that pressure. Answer-wise, looks like N equals 87.3 mole. Move that decimal over a little bit. Check my math. 0.873 moles of O2, which is what the problem, I do believe what they wanted. How many moles of O2? And that's not the moles, all the gases. If you put in all the moles, all the pressure, which would be 745, you would get the moles of the entire atmosphere. Alright, what are the mole fractions and mole percents of nitrogen and oxygen in the air when the partial pressure is 160 and 600 torr for nitrogen? Okay, so what are the mole fractions? We got partial pressures. So let's do this. Alright, it says 160 torr is the partial pressure of just the O2, and we have 600 is the torr, is the partial pressure of the nitrogen. Alright, so this thing wants a mole fraction. Alright, what is mole fraction? Mole fraction is equal to, let's see, for the O2 would be the moles of O2 divided by total moles. Alright, so in this sense they have not given us a sample size. We can simply set a sample size. Let's just say we have, alright, so we'll need to get moles, so we're talking PV equals nRT. I want to solve for moles. So N equals PV over RT. Pressure, again, I want to put just the pressure of this guy in here.
Please come to student services. Ali Kunin, please come to student services.
So I want to just simply put in here the partial pressure of just this guy. This is going to be 160. Now the volume was not set. Doesn't make a difference. I can set my own volume because this is proportional. So let's just say we have volume equals 1 liter. So 1 liter. R, because I'm torr, 62.4. Temperature was not given, but it's proportional as well. This is all really consistent. Let's say temperature is 273, 0 degrees Celsius. All right. And then all you would do here is you would simply do the same thing and substitute in the value for this guy, and you have the moles of each. Now once you have the moles of each, you would complete your formula. So let's run the math through here. So my moles of O2 equals 0.00939. Now the bottom is total moles. And I need to add together the moles both together. And I'm going to resub in this value, the 600. I get 0.035. Okay. And then we simply do the math. The total is 0.0446. So this is giving us 0.0446. Divide these two. And we get right here 0.210. And there is no unit really for this equals the mole fraction of the O2. And that's what they want. What's the mole fractions and mole percent? So it'd be, this would be the mole fraction, and then 21.0 would be the percent. And it says of nitrogen and oxygen. At this point, this is the O2. You could just subtract off 100 for this guy and off of 1 for that guy. And that would be pretty much it.